Hello, welcome to another Quarkus Club YouTube channel, a live demo or a live presentation today. I'm Igor de Souza, your host, and today we have a special guest to talk about a special topic. I'm kind of suspicious to say, right, because it's one of the topics of my interest. It's about Loom. So I will bring our guest here. Let's invite him to the stage. Hey, hello, Martin. How's it going?
Hi, everyone.
I'm pronouncing your name correct, Martin.
Yeah, Martin is correct.
And the surname is Stefanko?
It's Stefanko, but
Almost there.
on purpose, I will lose some symbols which are not very used commonly around the world.
Fair play. So, yeah, nice to have you here on behalf of the Quarks community or Quarks Club. Thank you again. Thank you for your time. As I said, the topic is really trending, really popular or controversial issue, if you like it. Is Loom the future? Is Loom going to makes reactivity die? Quarkus need to change something under the hood? Let's say, who knows, right? Who knows? All right, I let you. I saw that you shared the screen. I'm going to put here, so I let you follow up. As I said before, if you want to answer questions on fly or on the end, and we'll see how it goes, right? So,
okay.
Thank you again.
Well, I'm glad to be here. So I suppose that I can take over. So hello, everyone, once again. So today we are going to talk about Project Loom and especially how Quarkus approaches or how it already approached Project Loom. So just really shortly about myself. So here you have that strange letters which you probably don't understand. So my name is Martin Stefanko. I work as a software engineer at Red Hat, mainly on Quarkus and JBoss ZAP or Wi-Fi application server. So like all middleware technologies that we have in Red Hat. I also lead the Java user group here in Brno in Czech Republic. I am a microprofile committer, and currently I'm also writing my first book, which is called Quarkus in Action. And actually, I have some free codes that I can give away. So if you will have any questions, and I will be able to find you online after the lecture, I will have some like full discount for the book, which you already should have all the chapters available, I believe, but it's still not yet released. It will go into print this fall. And if you want to find me online everywhere on GitHub, Twitter, or X, on Mastodon, I am xstefank. Okay, let's dive in. So typically I will start this talk by a question to audience, but since this is online, I just answer this to yourself. If you really think that Loom is the future of Java, I will keep my answer for myself, and we will get to this by the end of this talk. I want to start by basically going over the whole thread processing in Java as it was created 29 years ago, like last week or this week, Java turned 29. So I will start with like traditional thread processing before we had Project Loom, before we had reactive programming. Before that, we would write a simple code with, for instance, blocking I/O in form of remote HTTP call like this. So basically, in my application, I would basically just call my HTTP endpoint, and basically then I am blocking the thread which was allocated for this request. So I will start again because I probably missed the point. When you will basically, when someone will call this get method, this call method, Quarkus or any other application server will allocate a single platform thread, real operating system thread for the execution of this request. And you are holding this request for the whole duration of that request. That means that if you will execute some blocking I/O operation like remote HTTP call, accessing disk, sleeps, etc., basically you are not doing any actual work. So you are not utilizing the CPU, but you are still holding that particular thread which was allocated for you. So here, while you are waiting for that HTTP call to return, you are basically just holding that thread and not doing anything. Once you will get back the response, you can continue processing and do whatever you want with it. And basically, once you are finished, you will basically return the thread back to typically some thread pool so it can be reused by other requests. If we put this into a visual perspective, and I will use server and remote service for my example, when I will get request one to my server, basically I will allocate that platform thread, real operating system thread, and I will start executing my request on that thread. Once I will get to the point where I need to execute my blocking IO, like my remote request, I will basically start executing it. And for the duration of that call, I am blocking that platform thread which was allocated for my request. Once I will get back the response from my remote request, I am continuing my execution. And once I'm done, basically I'm finished. If I have any more requests coming in the meantime, the only thing, because this thread, as I said, is like in sole possession of request one, the only thing that I can do now is to allocate another platform thread or take another platform thread, which will be allocated for request two. And I will do exactly the same thing. So for the duration of remote request on my request two, I am again blocking my platform thread two, and once I'm finished, I'm basically finishing. As I mentioned, once that request is finished, it basically returns that real platform thread back to some thread pool, so it can be again reused by other threads. So if I have a request 3 coming after request 1 is already finished, I can reuse the same thread to execute it. But you already can see that we are limited because we are basically, for the duration of that blocking IO operation, just holding the resource, even if it could be utilizing CPU for something else. And of course, we continue doing this until we finish. Before we dive into Reactive, I actually prepared the code that I am showing you in the slides in the real Quarkus application. So I have my example client and my call application, and just with a little bit of code on top of that, because I want to also count the concurrency of how many concurrent requests I can execute, basically by call, how many times concurrently I can execute this method. And for that, I am misusing reactive messaging, or now it's only called messaging, sorry about that, which will basically just increase and decrease some counters, and I'm just keeping the maximum. And other than that, I'm doing exactly the same thing as I was doing there. I am executing a blocking get operation, and then I am basically just calling some uppercase. I have this and I don't have this running, so I will run my application in dev mode because it's easier to change after we will need it. You probably know that if I press W inside this terminal, it will open a new tab in my browser where basically it opens my application. And here I am already having prepared this /blocking call on which will basically generate 1,000 requests. But since I know that this takes forever and I don't want to block you forever, I will just change this to 500 because this already shows what I wanted to show. You see that we executed all 500 requests, but the maximum concurrency that we were able to achieve is only 200. And why is that? Because if we go back into the terminal where I'm running the dev mode, you can see that I'm executing all my requests on a real platform threads. In Quarkus, executor thread is basically a worker thread, real platform Java thread. And here you can see that the numbers will go up to probably 200. Yeah, 200. I saw somewhere there 200. And this is because by default, if we go into application properties, you will see that Quarkus will actually limit the number of threads that you can create to 200. So if I change it to 500 with this Quarkus thread pool max threads, and of course I can just reload my application, now I can, without ease, run more requests because my machine is powerful enough to create 1,000 operating system threads. But of course, it's already taking some toll. And probably if you will check my CPU utilization down here, you will see that I am getting a little bit of more spikes because I'm creating 1,000 requests, 1,000 threads, and we can see that now I'm really getting into 1,000. So, of course, this can scale, but creating real operating or platform thread in Java is typically expensive operation. So you need to allocate some memory for it, and it also takes quite some amount of time to just allocate the thread, also context switching, etc. So you cannot create unlimited amount of real platform threads. Typically, on my machine, I can get into like 15 to 20,000 threads until my memory just runs out. So this doesn't really scale. This is why we basically, until we came with different ideas, we just used to pool threads. So we created a pool of threads, which basically you could allocate the thread for a particular request. And once you are finished with it, you will return it to the pool, and any other request can take it again from that pool. But you are limited by the size of the pool which you will allocate. In my case, now I'm limited by 5,000, but you see that by default, this is limited to 200 because this is quite dangerous. And I know my machine, but definitely you need to test this if you want to play with this kind of configuration, you need to test it inside your production server because it can end up badly. Okay, so moving back to the slides. So because people realized that this is kind of an issue, because for the duration of the request, we are wasting the resources which we allocated for the request, we came up basically with the idea of reactive programming. In reactive programming, the way how you write the code changes, and probably since we are in Quarkus Club, you are familiar with some form of reactive programming, so you probably saw Uni somewhere already. Basically, with reactive programming, you are writing something which is called continuations, which basically means that if you execute blocking operation or blocking IO, you are not blocking the thread which executed it. You basically will unmount its execution from a real platform thread, and you will register a code which is called continuation, which is a code which will run after you will get the result from that previous operation. And this is IO signal, which is basically we just registered that this string to uppercase should be executed by you will get result from this reactive get. Of course, in such an easy or small example, this is quite still readable and very similar to the blocking example. But when you will get into more complex reactive pipelines, I agree that it can get a little bit more complicated, and it can also be a little bit more problematic to debug or basically to find any problems in your pipelines. But of course, it also depends how complex your application is. Because this is not really that much adopted approach, but it's still approached more than you would probably expect. Basically, JDK came up with the idea of Project Loom, but we will get there in time. So if we take our same example, sorry about that, if we take our same example now in reactive programming, basically now we have threads which are called event loops, and we have really small number of these event loop threads. By default, I will have only 2, which are the actual platform threads, real operating system threads allocated as we allocated them before. But when we will get now with reactive programming requests, basically we will start executing it on any free event loop. So yeah, I have only one event loop in this example, so I will start executing my request. Once we will get into that point where we need to execute the blocking IO operation, basically we will just unmount that execution of the request one from the event loop, and we will basically leave it be. If there is request 2 coming in the meantime, basically we see that the same event loop can be now reused, and we can start executing request but on the same thread, same platform thread as we executed request 1. When we will, and again, we will get into the point when we need to execute blocking IO, and again, we will unmount that execution from the event loop. When we will get to the point where that first remote request is returning back, or we have a signal that that IO was completed, basically we will again find some free event loop. And this is also important to note that this doesn't need to be the same event loop as originally executed the request. It's just easier, for example, to show it on a single thread. Basically, if we have now a free thread, free event loops, we can continue executing it on the same request. And you can already see that for the duration of the remote request, we are not wasting resources because we are executing the computation of request 2. Exactly the same thing when we will get back signal from remote request 2, we can continue executing it on the same event loop thread. Of course, if there is nothing to execute in the meantime, if you are blocking somewhere on IO operation, it doesn't mean that you need to find something that will fit into that slot on every event loop, but it doesn't really matter because if we don't have anything to execute, we don't need to do anything. But if we have, we are better utilizing that single platform thread. So you can already see that this will not give you any more performance from your application. The whole idea of reactive programming and also Project Loom is basically just to give you better utilization of the resources that you already have, because we are not blocking anywhere. And of course, this continues forever. So if you ever tried reactive programming with Quarkus or with anything else, there is a single golden rule, which is never ever block the event loop thread, because if you will block this, basically this whole model goes sideways. Actually, if you try to do this in Quarkus, and probably we can already move to code. So I already implemented that same example now with reactive programming. And in Quarkus, basically, whether you are executing on event loop or on worker thread, on the platform thread, is decided by default by the return time of the method, which is being executed. If you use just normal return types, we expect that this method is blocking. If you return reactive types like uni or multi, we expect that this code is non-blocking, and so we execute it on event loop by default. But there are also annotations blocking and non-blocking if you want to change this, because some use case which you might run into. You can also see that I changed this to some async invocations because I also need to plug my concurrency tracking into that pipeline. So it's already registering 2 continuations. After my reactive get, I am executing my map operation to map to uppercase, and I'm also invoking this decrease async. So I have my concurrency tracking, because I cannot execute it really after basically I will make this non-blocking operation. I want to execute that decrease only after that request is actually finished. This is why I need to register it as, I can probably close this. I need to register it as another continuation. So if we go back into our application here, I also have, let's reset this. So we have clear shield, this reactive endpoint now. And you will see that if I execute this, I am getting very close to that amount of request concurrency that I basically executed. And if we check the logs, you will see that I am executing basically everything on 1. And probably if I scroll, 2 threads. 2 event loop threads are able to execute basically the same amount of concurrency as I did with 1,000 threads before, almost the same. So you see that we are way better in utilizing the same resources, because I'm basically doing the same amount of work in almost the same time in like a fraction of number of threads. Okay. One more thing that I want to show is that if I would be daring enough and in my non-blocking method, I would try to block, let's do 5 seconds. So I am blocking for 5 seconds. And if I now execute this, if I execute this just manually, so we have only one request. Now I'm blocking that event loop thread for 5 seconds. And you can see already what I meant. This is not important. We can close this. Quarkus can detect this, that I am blocking that thread for some duration, which is by default 2 seconds, I believe. Yeah, 2 seconds. And it will tell me that this is not something that I should be doing because, as I said, that whole idea of reactive programming is that this event loop is never blocked and I'm blocking it. So it will tell me that probably I want to execute this part of blocking code to that worker thread, to the real platform thread. And basically, I know that I'm doing something wrong. So now you have the idea, and I can remove this, so we don't need to keep it here. Let's go back to slides. Also, if you have any questions, please just ask them, and I will probably be able to see them on inside the chat if my phone will reload it, because I'm still at work. So you need to give me a second, or maybe you can tell me if there are any questions, because I cannot find the chat now, of course, on my phone. Because it will be better to ask the questions. Here it is, live chat. Yeah, I see. Okay. So if you have any questions, please ask as we are going. Okay, let's go back to slides. Now we are getting into, of course, now we are getting into the real important stuff, virtual threads. So virtual threads came with as a preview with JDK 19, sorry, not 11, 19. And Quarkus was one of the first adopters of virtual threads. So basically, you can use virtual threads since they were introduced to public. In Quarkus, we made the decision to not enable or basically give you a configuration that will move execution of all your code to virtual threads, because reasons which we will get into in a minute. So basically, if you want to use virtual threads, unfortunately, now in Quarkus, you need to annotate every method or class which is run on virtual thread. Of course, if you annotate the class, all methods in that class will be run on virtual threads. This annotation basically can be used almost everywhere, also in messaging, for instance. So in your reactive code, you can also run parts of your reactive pipelines on virtual threads. And basically that's it, because as you can see, we didn't change that first example, that blocking example in any way. Basically, I'm still executing my blocking remote operation, remote IO, and I am still blocking that virtual thread. But the whole idea is that now I am blocking only the virtual thread and not the real operating system thread. And I will show you in the image in a while how this is done. And of course, once this is finished, we are continuing in the same way as we use with normal platform OS threads. So how is this magic done in Project Loom? So we again start with our server and remove service. And now we have two types of threads. We have virtual threads, which are the ones that we are using. And we have something which are called carrier threads, which are actual platform, that operating system threads as we used them before. These carrier threads are actually used to execute the execution of the code of the virtual threads. So basically, any virtual thread needs to run on some carrier thread. And again, the same as with reactive and with event loops, it doesn't necessarily need to be the same carrier thread. But because of the isolation on the JDK level now, it shouldn't really matter. So when we will get requests to our application, basically what we will do, and now we need to switch a little bit our way of thinking. Virtual threads are very lightweight user space threads. They are cheap to create, cheap to switch between, and cheap to destroy. So the whole idea of how you should use virtual threads is more like fire and forget. No reusing, no pooling, nothing like that. So when we will get a request to our application, we will create a new virtual thread because it's cheap, fast, and we can do it. And basically, we will start executing our request on that virtual thread. What this really means, as I already said, we need to find a free carrier thread, which will basically start executing this virtual thread one. When we will get to that point when we need to execute blocking IO operation, basically we will unmount the virtual thread execution from the carrier thread, and we will continue to block, but we will block only the virtual thread. So you can see that carrier thread is again free to be reused by any other virtual threads, basically. If I have another request coming in the meantime, again, virtual threads are cheap. So I will create a new virtual thread, which will start executing my second request. And the same thing, when I will get into the point where I need to block, I will unmount it from the carrier thread, and I continue to block only the virtual thread. So you see that, again, carrier thread can be reused by anything else. If I have a response from that first IO coming in the meantime, I will basically indicate that I need to continue the execution of virtual thread one, and I will find some free carrier thread to continue this execution. Once virtual thread is finished with its execution, I will basically leave it to be garbage collected. You are not keeping any form of basically pointers to it. Basically, once the execution of virtual thread is finished, it's going away. The same thing when I will get response for my IO2, I will again finish the execution, and the virtual thread 2 is destroyed. If I will get the same thing with virtual thread 3, we can go a little bit faster. Exactly the same thing will happen. Once I'm finished, I will destroy this, and we are continuing. So probably you can already see that if I put this side to side, this upper part actually looks very close to that traditional normal platform thread processing, which is that whole idea, because from your user perspective, you want to have the same experience as you had with normal threads. And this bottom part looks exactly as that event loops, as the reactive programming that I showed you before. So you see that whole idea of Project Loom is basically to take the complexity of reactive programming from the user space to the JDK itself. And basically, you can still continue writing the same code, the same imperative code, same blocking code as you are used to, and you don't need to bother with continuations. The continuations are basically handled on the JDK level. And of course, what can go wrong if it's not the framework which is controlling the allocation of threads? Basically, there is a bunch of problems that can basically come up with virtual threads. So it's good to know that there is nothing like a free lunch. So this is why Quarkus actually doesn't have a global switch, at least for now. And here is the list of the individual problems that we will go through one by one, so we can basically start. The first problem that can happen is pinning, which is actually the event inside the JDK itself. And you will see it in a minute. Basically, what pinning is that sometimes when you block your virtual thread, you cannot unbound it from the carrier thread. So for the duration of blocking of your virtual thread, you are also blocking that carrier thread. And again, cycling back, carrier thread is behaving as event loop. And you remember that golden rule, never ever block the carrier thread, because the whole model goes sideways. So this is a problem. Actually, let's go into our application. Yeah, and I forgot to show you virtual threads, so let me fix that. So I have also that same example with virtual threads. The only difference to my blocking resource is in this run on virtual thread annotation. And of course, if I call my virtual, I don't know what this is, virtual, hopefully I am getting exactly the same expected behavior. And if I go into my application, you should see that I actually created almost 2000 virtual threads. And why is that? Is because I am actually misusing virtual threads to generate that request. So one or recommended way how you should use virtual thread in Quarkus is either annotating it with run on virtual threads, but of course, many times when you are dealing with threads, you are using executors and not creating the threads manually. So in Quarkus, if you want to have an executor for virtual threads, you have this at virtual threads annotation, which will basically inject virtual thread executor for you, which gives you a slightly better executor because it, for instance, names your virtual threads. So you can see that my virtual threads are named Quarkus virtual thread because by default, virtual threads are not having any name, which is quite hard to debug when you will start dealing with this. So you can see that I'm actually misusing this to generate requests to my application. But basically, this is more or less it. I don't need to change nothing else inside my code. Okay, so when I want to talk about the issues with virtual threads, I want to keep it very simple. So we will basically see the actual issues. And for that, I will be writing basically a real manual main application so we can get the idea. So bear with me. Hopefully this will be understandable for everybody. So I have basically this virtual Java, which is not printing anything. So I can start playing with these manually so we can see the issues because they are quite hard to reproduce on a scale, but you will see in a minute. So one way how to create a virtual thread is basically you have this new static method on the thread class of virtual, which can basically just do start. And here I can do my lock thread a start sleep for 100 milliseconds and lock not thread b start thread a end. And of course, if you want to see actually something happen, you need to actually wait in this main thread for that virtual thread to finish. And now, oops, if I run my application, we should see two logs, thread A start, thread A end. And I'm using this glorified log statement that will also log, where is it, current thread. So we can see actually on which thread we are running. And you can see that I waited for almost like a little bit more than 100 milliseconds. The interesting part is basically this actual thread. So we can see that I am running on some virtual thread, which is running on some fork join pool. And we will get into that in a minute. The idea that I want to show you is that basically if I would call here, oh, sorry. Let me do this. So log, let's do thread current thread get name. You will see that if I run this application now, I am not getting anything unless I will manually name. Let's call this Quarkus Club. My threads, I will not get any name. So now I am getting Quarkus Club. Of course, this is, again, not something that you will write manually and probably, okay, I will do one more because we have good time. So let me do thread B, thread B. Let me remove thread current thread because we don't need it. Not here, and thread B end and thread B join. So now if I execute this, and hopefully we will get what I wanted to show you. Now I can show you basically that idea of how this execution happens. So here you can see that thread A is executed on worker 1 and thread B is executing on worker 2. So what this fork join pool 1 is actually is the pool of the carrier threads. So this is the actual platform thread which is executing my virtual thread. And my virtual thread is actually virtual thread 30 and 28 out of the box. You can already see here that we have two real platform threads executing simultaneously our two virtual threads. And they are actually executed at exactly the same time, as you can see here, which is like exactly what we want. If I run it a few times more, probably, because I need a little bit of luck. Of course, I will not get luck. Now I have luck. So you can see that thread B was executed on worker 2, and it was finished after we basically unmounted it from carrier thread, and again indicated after our IO operation, after 100 milliseconds, that we want to execute it again. Basically, it landed on worker thread 4. So this is just what I wanted to show you, that basically you can end up on something else. Basically, of course, you will never probably create threads like this, but it's good to know that this exists. Also, now there is this thread of platform if you want to create a normal thread, but probably you are using executors to create your threads. So for that, you have this new virtual thread per task executor on the executor class, which will basically give me an executor of virtual threads. And I can do, probably I could have copied it before I commented it out. It doesn't matter. You can do it fast. Now, what I can do is, instead of this start, I can do executor submit, and exactly the same thing. It just now returns future instead of thread. But it's not such a big issue. What is this? Okay, there we are. And I will do the same with thread B. So executor submit, and this will be F2. Okay. Of course, now it's future, so I need to change this to get the results. Come on, get. And basically, if I run this and I didn't do anything wrong, we are getting exactly the same thing. So we are still executing at the same time on 2 virtual threads. Now we can get into that potential issues. And again, the first one that I want to show you is this pinning. So what will happen? By default, probably I can show it like this. Pinning happens as an event in 2 cases. Basically, when you hold a monitor lock, so synchronize block or method, or if you have a native call in your stack. So if you have a native invocation anywhere inside your call stack, you cannot unmount also the execution from the carrier thread. And this typically happens in basically native library call or with the new foreign function calls. But basically, I think Clem and Escoffier counted inside the core Quarkus platform, you have only 13 native libraries. So yeah, count your chances. Like, what are your chances that you are executing some call path that is actually having this in your call stack? But for now, this also happened with the synchronized block, so it's very easy to reproduce. So basically, before we move on, and I don't know if I have it. Yeah, I have it later. So I will jump a little bit in my slides. We will get into carrier thread scaling very shortly, but I just want to show you these 3 properties, which can be actually used to configure JDK or to configure that fork join pool, which is actually used for that carrier threads. So I have basically this virtual thread scheduler. Parallelism is the default number of threads created in the fork join pool. Max pool size is max pool size. Sorry, parallelism is by default the number of cores on your machine, which in my case is 16. Max pool size is restricted to 256. And minimum runnable is basically half of parallelism. So what I can do now, and probably I can close this in the meantime, I will show you something after that. I already prepared basically these 3 properties on my virtual Java program, where I will basically limit the size of that carrier thread pool to 1. So I am setting everything to 1. And now, as you would expect, if I run my my virtual threads, they are all run on worker thread 1 because there is only 1 carrier thread. Also, one thing which I forgot to show you, because again, we don't have any names for the virtual threads and this number is hard to follow. Basically, I will show you the hack that Quarkus is probably doing also in the background. So if I create basically a thread factory like this, and let me do it like this. Start at 0, and I will call factory. I can get back thread factory, where I can now change this new virtual thread per task to new thread per task executor, and I can pass that factory inside it. And if I now call my my application, you can see that now I'm basically setting names in increasing manner to my application. So this is how you can name your virtual threads in some different way if you want to. But this is also done by that injection, as I showed you, which I'm using to generate requests. Basically, I'm still creating virtual threads and I'm just giving them some name. Just it's good to know that something like this exists. Okay, and it also makes it a little bit easier for us to track which thread is which. So back to our application, because I'm limiting the size of that carrier thread pool to 1, of course, everything is executed on the same carrier thread. And if we check the times, you can see that basically I am executing still basically both virtual threads almost at the same time, and I'm also finishing them on the same time, because what will happen when I will start executing the thread A and it will get into my IO operation, it will be unmounted from that single carrier thread worker 1, which is now able to execute my thread B. So we are here. And again, when thread B will get into its IO operation, it is again unmounted from the single thread. And when my sleep finishes, thread A finishes, and after that, thread B finishes. Of course, this is nice and it works, and we are still utilizing that single thread in basically the best possible way, because we are always executing something. What will now happen if I just synchronize this around the sleep, and I will try to execute this again, is that it will still execute on one thread, but you can already see that I am executing thread A first, and only then I can execute B, and we can also see it on the times. So basically you see that because I just wrapped that I operation in synchronized block, we are now not able to unmount the execution of the virtual thread A from the carrier thread. So it's holding it for its 100 millisecond. And only after then I can move to thread B execution. Basically, this limitation is something which should be removed in JDK 23 or maybe later. So it's not that it's that critical, at least, but right now there is nothing you can do about it unless you will, and maybe I'm going a little bit fast over myself. I want to show you one more thing, and of course I stopped the dev mode, because why not? Actually, JDK, because as I told you before, this pinning is an event, it's a method call on the thread itself. You can basically catch that event as a JFR event with this JDK trace pin threads full short. So if I copy paste this into my execution, and I know that I'm now pinning my virtual thread. So if I go just here and I will put -d and let's do full. And I will execute my program again. We will get this really nice printed exception that I am basically, where is it? Reason monitor unpinned, and I can get directly into the point, not here, here, directly into the point, this one, where I can find my synchronized block, where I'm executing the pinning. Actually in Quarkus, because I have here also this problem resource, which is running on virtual threads, and currently it's passing everything. So if I run my tests inside dev mode with R, you can see that I am executing basically tests over the problem resource, and now they should be passing. They are. But if I introduce this pinning of carrier thread, which is exactly the same thing, I'm just wrapping sleep for 1 millisecond in synchronized block, If I now rerun the tests, and they are already running, you can see that I already get one failure so far. And you can see that basically in Quarkus, we can catch that JFR event for you. And we can tell you that if you basically annotate your test, where is it? Annotate this test as virtual thread unit with this should not pin annotation. Basically, we will watch for the JFR event, and if we catch it, we will basically fail your test. So at least in this kind of way, you can automate the detection of that pinning event. Okay, this is actually coming from library, this IO Quarkus JUnit 5, JUnit 5 virtual threads, if you will be looking for it. Okay, where was I? Virtual. So we can catch these virtual threads, but actually if I want to do it a little bit more complex, so I will take this whole method into, let's extract it is good because it's extracted. And of course, I can do the same thing if I put the whole method as synchronized. So I will still get my pinning event now just in different place. And my application behaves exactly in the same way. I will actually now remove that flag because it's just printing a lot and we don't need it because we can see what I mean also on this time. So we still can see that that one single carrier thread is blocked for 100 milliseconds until we can move to thread B, virtual thread B. So how to fix if you run into any of these cases? Synchronize block is easy because all you need to do is to remove synchronize, and you need to introduce this static reentrant lock, which will be my lock, new reentrant lock. And to get the same functionality as before, I just need to do this, wrap it into finally, and here I can do lock, unblock. And now I'm getting functionally the same application. And as you can see, I am no longer pinning. So fixing synchronized block is very easy. Just rewrite it to reentrant block. But as I said, this should be fixed with JDK 23, but we will see if this is going to happen. So let me just put this code back. I will just keep it here so you have this after the talk. But for my examples, it's better to see it in one place. So now I'm back in the case when we are not pinning, not doing any kind of magic. Or, well, let me do one more pinning because we have a little bit of time so we can play. So let me pin again. And I just want to show you a nice example. What will happen if I allow this fork join pool to have two threads at maximum? We are still starting with one, but I'm allowing it to scale to two. And now I need to try it. Well, I don't need to try it several times because you can already see that I was able to scale to two threads. And actually, well, I'm surprised that this is executing on the same thread. Because this is thread B. Okay, so thread B is, of course, not pinning. So thread A is pinning. But you can see that it's not pinning because we are finishing both threads at the same time. Maybe I will run it a few times more. So thread A is first. Of course, I will not get thread A first, even if I try. But you see that basically I can get around that because now I'm allowing that thread pool to scale to two. I go back to one. We are again serializing it on one thread. So you can see that this fork join pool of carrier thread is elastic. And actually, this is that test which we were running before. Let me go back to that application that we were doing, let me restart this. So this Quarkus dev, actually, I can show you a little bit of hex, and I think it's JF. I have this utility JF, which is basically just a glorified grep over JPS to find an application Java application ID. So you can see that my dev mode is actually that ID, which I'm looking for. And with JStack, I can now basically grab that worker threads, which are my carrier thread, and just WC minus L is counting them. So out of the box, as I told you, I am getting 16 carrier threads created because I have 16 cores on this machine. What will happen if I now generate that 1,000 requests to my application? Of course, everything passes, but check this. Just by generating that 1,000 requests, I basically already scaled my carrier threads to 42. And of course, this will probably go even more if I try it once more. No, now I'm basically handling it. It's already okay, but you get the idea. Probably I don't want to really play with this when I'm streaming on Wi-Fi and we can run into issues, but it's already showing my point. Because basically JDK is not catching up with the number of requests to create virtual threads. It can actually spawn new real platform threads, new real operating system threads, which is again that expensive operation, which takes a lot of resources, both in form of memory and in time. So just something to watch for. I will keep this running for a while, and we will go back to our command line application because I want to get to that after a while. So I think that pinning is now basically finished. Of course, if I would change number of maximum threads, and also I will start with 2 threads, I will always run on 2 threads because I'm now executing 2 tasks on 2 threads. I have no issues. The only issue is when you will run out of that threads. Okay, you probably get the idea. So let's go back into non-pinning green scenario case where I'm getting my 16 carrier threads in the background. Basically, the other issue that can be found inside with virtual threads is monopolization. Very similar case because you are now again blocking both virtual thread and the carrier thread. Just this time you are just doing it because you are executing actually something on the virtual thread. So you are executing some computation, which is basically unless there is that IO event, basically JDK cannot unmount your virtual thread from the carrier thread. So if you just continue computing something, you just continue computing it on that carrier thread. And exactly the same issue. You are now unable to unmount that virtual thread 1 from the carrier thread. And if you have more requests coming into your application, the only thing that the JDK can do is to create more carrier threads to handle the new virtual threads. So basically, this is exactly what happened inside my dev mode when I was trying to execute the 1,000 requests. I'm not actually pinning because I am executing remote IO, so it is successfully unmounted. Just the amount of requests of how many virtual threads should be created is not possible to handle with 16 carrier threads. So JDK scaled that fork join pool to 42. But I just need to give it that credit because if I left it running for a while, and hopefully now we already can see that after a while when they are not used, when the carrier threads are not used, that fork join pool can also shrink. So just to give it the credit back, it can scale, it can also shrink. But exactly the same issue, if we don't find an IO operation, we cannot unmount the virtual thread from the carrier thread. And of course, if I want to basically simulate that inside our application, I can just do very long computation here. And just to be able to compile, if I now basically block, sorry, I need to limit this to only 1 thread. If I now block the execution in my virtual thread A, and I have only 1 carrier thread, of course, I will never give a chance to thread B, to virtual thread B, to actually find a free carrier thread. But if I will stop this, if I will just basically sleep here for 1 millisecond, so I will create that IO operation, which is basically meaning that I can, at least for 1 millisecond, unmount my virtual thread A from that single thread. Now you will see that my thread B will get its chance on worker thread 1, on the carrier thread 1, and it will execute after 1 millisecond plus or minus. And it will execute. And I am now continuously blocking and unblocking, mounting and unmounting my virtual thread A, but we can continue. So this is only the issue when you are blocking basically with computation, which is not stopping. Of course, there is also this, because I get this question all the time, yield method, which will give you exactly the same behavior. Just keep in mind that this is not recommended to use in production. This is more intended for testing and debugging. But yes, there is a yield method on thread. And this is more or less it, because like this is this is basically nothing that we can or JDK can do something about. If you just execute long-running computation on your virtual thread, you will block the carrier thread. But as you saw with reactive programming, with that event loop, if I block that event loop, it's something which we can actually in Quarkus see that you are doing, and we can throw that exception to actually tell you that probably this is not something that you want to do. With Project Loom, with virtual threads, we don't have any kind of hooks like this. So basically, unless the JDK would provide for us some kind of like monitoring of the execution over the carrier threads, we basically cannot warn you that you are, like, not so nicely said, shooting yourself into the leg, because in your mind, from your perspective, you are just blocking the virtual thread, but you don't see that you are actually scaling the virtual threads in the background. And this is the main issue that we want to get into, because yeah, this is just a different example of the same. What is the main issue with carrier threads is scaling, because if you will pin or monopolize that virtual thread, that carrier thread in the background, JVM will create new real platform threads, new real operating system threads. They will be not created probably in the same rate or frequency as it used to if you just execute it with normal traditional JVM processing. But the same issues still persist. You can still spend memory and time on creating real platform threads, and you might eventually run out of memory if you will be not careful. So let's go. Yeah, I already showed you how to limit this. If you need to, of course, you can also limit it to more threads. This is up to you. Like, definitely, you don't need to be limited by 256. This is just some default. And before we will move into that, I will probably, I think that I already showed you everything, because you got the idea. Maybe one last example. How much time do we have? Oh my God, I'm already at the top of the hour, so I will not show you. But you'll probably understand that if I would give it just 2 threads, then I can execute thread B also when I'm monopolizing thread A, just because I have 2 carrier threads. Last thing, which is also something that we need to watch for, but it's again not something that you probably need to watch for, is thread locals. Because if you are familiar with how enterprise Java is actually working in the background, there are many things stored in thread locals. Why? Because we had these thread pools. We control that thread pools. And if we know that the same thread is, for instance, reused by multiple requests, which needs to access the same transaction or do some mapping, for instance, JSON, and we have some really expensive objects which are taking a long time to be created, and they are taking a lot of space, we actually store them in thread locals on purpose, so they are created only in the number of threads in that thread pool, and we don't need to recreate them every time with every single request. But now, since you are basically executing multiple virtual threads on the same OS thread, on the same carrier thread, JDK is actually forced because thread locals are fully supported in virtual threads. So you will get the same code running in virtual threads, but every virtual thread will copy the value of that thread local. So if you have expensive objects, you will now copy it in the numbers of virtual threads. And of course, you can have billions of virtual threads on a normal machine, and this can run out of memory very, very fast. I don't really have time to show you this, but you probably can understand that I will just get 2 thread locals created for 2 virtual threads, even if I limit that carrier thread pool to 1. Yeah, I already said this. And last but not least, you need to realize that when you are writing code with virtual threads, you are actually writing concurrent code, but it doesn't look like it, because typically you are writing the same code as you did when you had 1 thread for the whole duration of the request. So just keep this in mind and use thread safe variants of classes. And with that, we are getting to the end. So after all of this, I also like to ask this question again: Is Loom the future of Java? Typically, I have more hands up, so decide for yourself. I personally think that yes, Loom is the future of Java, just we are not there yet. The actual issue is typically not basically something that you as the end users need to take into account, because I already talked about this. Thread locals also have a new experimental APIs called scope values, but we don't have time to dive into that. Basically, the issue is that the most problems will lie in the frameworks, runtimes, and in the libraries that your code is using. So like transactions or that object mapping, etc. So basically, I believe personally that the Java ecosystem needs to catch up. And this is not something that you can force or basically you can do overnight. So this will eventually take time. And I personally believe that when we will reach this point as a community, Quarkus will provide this global switch, but this will take a few years, in my opinion. So if I ask this again, I personally believe that yes, Loom is the future of Java. But to answer the question from the beginning, I personally don't believe that it will kill reactive programming. I still believe that there will be a really small percentage, up to 5%, in my opinion, of applications like API gateways or really high throughput applications, which will require that control of over when you will basically unmount your execution from that real platform thread. In Reactive, it's event loop. And if JDK will not provide this kind of hooks for us, I believe that some people will still opt for reactive programming. And with that, that will be everything from my side. And I just want to show you here that here you have QR codes for slides and for code. I will push a new branch, Quarkus Club 2024, into that repository here. And you can also see down here the QR code for 45% of our book, which we are writing with Jan Martiška, called Quarkus in Action, which I mentioned in the beginning. And now, if I have some time, I will take questions. Igor, do you want to read them, or should I just like take it myself?
Okay, I'm back.
Okay.
Yeah, you can go and answer yourself. Let me. Do you have some questions?
Okay. So
here. Does the pinning happens when using entrance lock?
no, this is actually that case. Yeah, I already see that Philip said answered yes. Rentran lock is actually that API which will not cause pinning. The second question.
This one. How it's current adopter of virtual threads in big tech companies? Good question.
To be honest, I don't personally know about anyone around our space that was very, like keen to jump headfirst into virtual threads. But you know that one of the biggest competitors of Quarkus actually provided a global switch right with JDK 21 when virtual threads became a stable feature. So yeah, we'll see. The whole idea of this talk is just to give you basically something to think about, because as you can probably see, the issues that I was describing, you will not find when you are developing your application or testing on your machine. The issues which I'm showing you, you will actually find on your peak traffic, probably before Christmas or Black Friday or something similar like this, where you really don't want your applications to go down on out of memory errors.
Fair
Okay.
play. So, Martin, thanks so much again on behalf of the Quarkus Club community. Thank you for your time. It's amazing. Uh, I guess I guess no, right. The video is going to be on YouTube, right? You can watch on demand. Thank you for everybody that was watching live. If you arrive here, and in case you don't know what it's about, Quarkus Club is a Discord chat group. We talk about Quarkus, right? Sometimes even bad things about Quarkus. Why not? We can say whatever you want. It's a friendly community. You can talk about whatever you want. Even if you want to advocate about the Quarkus competitor, we don't care, right? Everyone can talk whatever they want. Java for friends, for fun, for talk about Quarkus, of course. And if you want to get in touch with Martin, he's there. You can ping him, poke him there. He's going to answer your questions if you have. If you're not, you can leave the comments here. And with that, thank you, you guys, for watching. And keep posted. We are going to have more presentations and more people soon. So thank you.
Just, I also want to thank you for having me. It was my experience. Thank you, Igor, for organizing this, and hopefully you learned something.
Take care. Cheers. Bye bye.
Bye.